The U-2's replacement was equipped with 4 large equipment bays to handle a wide range of specialized reconnaissance and surveillance gear. Mission equipment included side-looking radar, a terrain objective camera, 2 operational objective cameras, 2 technical objective cameras, and infrared mapping, mission recorders, and an EMR system. The airframe is essentially a blended body and delta wing built around 2 huge engines. The long forward fuselage performs a number of aerodynamic functions. Its flat profile helps the Blackbird achieve a low radar visibility while retaining plenty of room for fuel and payload. The chines on the fuselage effectively make it act as a lifting surface and help improve directional stability. The enormous engines are positioned midway out on the wing and are housed in nacelles that have unique intake systems to control airflow. This is a critical factor in generating the plane's amazing power. Because of the Blackbird's speed, its wings are very thin, and a large part of their area is taken up with a honeycomb of fuel storage. But most of the fuel is carried in 5 tanks that occupy the majority of the fuselage. It's worth noting that in 1958, when the plane was first being developed, even the most advanced fighter designs of the day were flat out at Mach 2. They had ranges and operating ceilings that were hopelessly short of the espionage requirement. Everything about this new plane would be revolutionary. There would be new materials for the aircraft's parts, and even the machines to make the materials and parts would have to be developed from scratch. Lockheed had some experience with titanium fabrication, but this would be only a starting point for the metals needed for the job. The plane would have to withstand very high temperatures for long periods. Different areas of the skin would be between 800 and 1100 degrees Fahrenheit at Mach 3. As a result, despite the expense of the material and the research and development costs of inventing it, around 93% of the plane is composed of a titanium alloy. Of course, metals designed to operate under extreme conditions require even more extreme conditions to fabricate. Some of the major parts had to be shaped in a huge press designed to operate at 1500 degrees Fahrenheit. No such press existed before the need for parts for the Blackbird, so it had to be developed. In fact, the company would go through countless experimental processes in developing the aircraft. Many samples were produced, but the standards to be met were so rigid that a high proportion were rejected. Eventually, parts of reliable strength and integrity were produced, but only after much anxious trial and error and an undisclosed but presumably very large expenditure. Hot forging of the metal in special ovens and presses was only the first step in the processing. These shapes were in effect rough outlines of the parts. The forgings then had to be machined to extremely fine tolerances. The milling machines were advanced designs, tape-controlled early robots with special cutters developed by Lockheed to handle the metal. The cutting fluid was new too. One of its features had to be that it would not corrode the titanium alloy. At each step of this plane's development, everything was either new or specifically adapted, right down to the smallest factors and the most routine processes. Finished parts then moved into sub-assembly processes. Once again, everything was affected. Spot welders had to be specially adapted. Normal tools had to be recast in different metal. Nothing could be taken for granted. Early in the project, Kelly Johnson offered $50 to any one of his staff who could come up with an easy problem to solve. The impish humor barely disguises the core truth in the offer. The designers had to develop the aircraft in the abstract. Their function was, as much as possible, to foresee the implications of each consideration and to follow them until each problem had been identified and solved. They did this without the aid of digital equipment. They did it in the main with slide rules, pens, and bits of paper. There were many problems that arose, either unseen or half appreciated, during the course of early production. And there were flaws in the original A-12s that were dealt with in later models. However, the project ran very smoothly, and the success of the design team has remained a pinnacle of engineering achievement despite the passage of years. Each Blackbird came together as a series of sub-assemblies, with each of the major fuselage and wing components being produced in two sections. In part, this system was developed to save as many man-hours and as much assembly space as possible. Not only would the skin of the plane be subjected to extreme heat, the same applied to the interior. Wiring, which could be relied on at 900 degrees, had to be developed. The problems and solutions went on. Of course, no matter how good something looks in theory, there's always a need for more practical reassurance. A full-scale static test program was conducted. The kind of aerodynamic loads the aircraft would experience in flight were hydraulically forced, and the integrity of the design was studied. Individual components were also tested to destruction. Wheel assemblies were subjected to violent landings and various lateral stresses to test not only the landing gear, but also the tires and the brakes. Kelly Johnson had to accept with some bitterness that this masterpiece would not be produced in significant numbers. Only a few would ever be built, and they would be shrouded in the most effective security possible. Limiting manufacture to the SR-71 reconnaissance version ensured the mystery of the Blackbird, whereas the more public role of a fighter version might have allowed the crescendo of worldwide acclaim that the achievement warranted. The SR-71 was announced by President Johnson on July 24, 1964. It came as somewhat of a surprise to Lockheed because the SR-71 was supposed to be the RS-71, or the R-71. The R stood for reconnaissance, and the S ambiguously for strike. However, it was decided that the president's name would stick as standing for strategic reconnaissance. The SR-71 took off for its first flight on December 22, 1964. The flight was a complete success. Everything worked, and the pilots and mechanics were happy with the aircraft. The flight testing program proceeded well, most major problems having already been sorted out during the experience of the A-12 and YF-12 projects. The SR-71 progressed to acceptance tests at Edwards Air Force Base on August 13, 1965, and proceeded smoothly through testing and into service. Enough information about the Blackbirds continued to seep out to ensure that they became one of the most famous secrets in the world. Aircraft enthusiasts came to know enough about the plane and its capabilities to develop an appreciation of the achievement it represented. In September 1974, the Farnborough Air Show received a very special visitor. The SR-71 had flown from New York to London in 1 hour, 54 minutes, 56.4 seconds. Needless to say, this was a record. Aviation enthusiasts turned into fans, and film processors made a small fortune. Whenever the SR-71 turned up at an air show, it attracted a large crowd on its own. In fact, even the unfounded rumor that one would show up led to good crowds. The SR-71 spent so little time in public that this was understandable. On its way back to the U.S. after the 1974 Farnborough show, the SR-71 set another record, London to Los Angeles in 3 hours and 48 minutes. This included rendezvous for refueling in flight. In terms of local times, it arrived about 4 hours before it took off. Among other records claimed by the Blackbird was the flight on the 26th of April 1971, which covered 15,000 miles in 10.5 hours non-stop. This was the equivalent of San Francisco to Paris and back. The U.S. Air Force flew its SR-71s with the 9th Strategic Reconnaissance Wing, based at Beale Air Force Base in Northern California. They received their first Blackbirds in January 1966. In the next 24 years, they flew thousands of long-distance missions. Regular deployments were made to bases around the world, and flights covered most of the world's surface. Only top-of-the-line pilots were eligible to fly the SR-71. Requirements were about the same as for the astronaut program. There were no shortages of applicants for the job, however. There were no fancy escape capsules built into the aircraft. Kelly Johnson figured that the spacesuit the pilot wore was already an adequately controlled environment, and he concentrated on how to get the pilot clear of the plane at Mach 3. The ejection seat and parachutes inevitably had to be specially developed. Of course, there is no real way to test such an escape system. Obviously, you cannot simply take a Blackbird up to Mach 3 at 80,000 feet and shoot the crew out. At some point in the process, you have to accept whatever can be proved in adequate tests and deduce the rest. Those heights and speeds, what was achievable could at best be only partially guaranteed. Over the years, at least 11 SR-71s were lost for various reasons, and several crewmen died. A critical key to the Blackbirds had been the development of a fuel that would not burn simply because of the heat in the tanks, which, like the rest of the plane, got very hot at high speed. In addition, unlike virtually any other fuel, it had to be burnable at extreme altitude. Once the fuel had been developed, other problems seemed small by comparison. Soon after each takeoff, the plane refueled. In some aspects, Blackbirds are quite basic. To allow for the expansion of the skin at Mach 3 heat, there are corrugations, like an old Ford trimotor. In addition, to save weight and complexity, the skins are also the fuel tanks. Fuel actually leaks from an SR-71 constantly until it heats up, expands, and seals the tanks. And once hot, they stay hot. Even after a Blackbird lands, it is unwise to touch it because you may burn your hand. Time did not pass these planes by. Admittedly, the pilots continued to face a traditional array of round dials, but the surveillance system cockpit became home to a procession of advanced technologies. As computers became smaller, the functional capabilities of these big spies increased. They already presented the peak of operational capabilities. An SR-71 can survey 100,000 square miles of territory per hour. That has been a fact for a very long time. What it can glean from that area in that hour has, during its lifetime, increased considerably. When work on the Blackbirds first started, a basic fact to be accepted was that normal tools, which are coated in cadmium, would cause corrosion of the titanium alloy. Normal tools were out. This aircraft was a major step forward, and everything changed. Or did it? Kelly Johnson probably thought that he was starting a new technological race, that the next generation of aircraft, worldwide, would be Blackbirds of some sort or another, that the next step to higher speeds, or perhaps more refined maneuverability, would push past the new marks that his masterpiece had created. But that was not the way it went. The Russians developed small bands of high-speed, limited-range fighters, which were, in large part, drones, because their weapon systems were controlled from the ground. The pilot's only real function was to land and take off the aircraft and try to get the fighter in close proximity to its target. Apart from Soviet attempts at interceptors, Kelly Johnson's masterwork continued to rule the skies. What the CIA and U.S. Air Force did with them remains very secret, but there is enough information about their operational parameters and the equipment they could carry for one to spend hours in informed speculation about what they actually did. Back when Kelly Johnson's design team set to work on the problem of a U-2 replacement, they studied anything that could be considered a possibility. Among their early work was a proposal for a hydrogen-powered space aircraft, which Johnson described as a big flying vacuum bottle. This was well outside the technical ability of the time and was dropped. The plane that evolved bore no resemblance to a vacuum bottle. Super sleek, futuristic, the A-12. It should also have been outside the technical feasibility of its era, but has flown into history as one of the greatest achievements in engineering and one of the greatest aircraft ever constructed.